Okay, and finally we have a question here that reviews really all parts of optics, right? This is a little bit of wave optics and a little bit of ray optics, and also a little bit of experimental work. So we're given the results of an experiment to determine the index of refraction of a glass slab. And we use a laser beam, or we're told the student uses a laser beam to measure incoming angles and refracted angles. And we have a data table that records all those results for 5 trials. And immediately upon seeing the words refraction and determine the index of refraction and incident angles and refracted angles and all that, you should immediately think of one thing, and that's Snell's law. So we know that what we're going to be testing or comparing is Snell's law. Oops, not M. Right, so we're given these angles. And we're told that one of the indices of refraction is that of air, right? So this equals 1. So if we want to figure out something, we're trying to solve for this value. So if we want to do that, we don't need the angles, we need the sines of the angles. And so part A is just getting you to calculate, hopefully correctly, the sine of each of those values. And so if you do that, I'm not going to write all the numbers down. All you're doing is you're plugging in, right, for that first column. So the first row should look something, actually the first 2 rows I'll do, right, because you need the title. So this should be like trial 1, theta I was 30 degrees, theta R is 20 degrees. What you write here is just the sine of theta I. And if you plug that into your calculator, right, the sine of 30 degrees, you get that value. And then we need to do the same thing for sine of theta r. So you plug in sine of 20 degrees, and you get 0.34. So you have to label the top, right? That's this and this, telling me what you're calculating. Then you have to get the numbers right. If you're in radians mode, then you don't get the points for this, right? These are the units are written in degrees. If you see a degrees, your calculator has to be in degrees. Don't make that mistake. And so you fill out the whole table kind of in that way, right? Just by punching your numbers into your calculator to complete the data table. Okay, so for part B, we have some blank gridded paper there, and we need to make a graph using what we plotted in part A. So there are a couple different ways you can do this, but you know what your 2 axes have to be, right? The 2 things you calculated. So this will be sine of theta I, and this will be sine of theta r, right? And those things are unitless, so you don't have any units to write. However, you do need to make sure to number your axes precisely. You always start at 0 on both, and you don't get to do anything where you like cut part of the graph oddly and go like this is like 0.5 and you cut this one differently and you go to like 0.9. It needs to be evenly spaced all the way up, nice and linear. So for this, since I know sine can never be bigger than 1, right, I'd probably space it out from 0 to 1, and similarly in the other direction. So again, I'm not going to be able to graph it quite as precisely as you're expected to do. But, right, if I do something like this, 2, 4, 6, 8, 1, right, so that's evenly spaced with each spacing be about 0.2. Do the same thing on the y-axis, 2, 4, 6, 8, 1. And if you put your data points that you calculated out there, most of them are in about the 0.5 range. So that's like, one of your data points is like right there-ish. And the farthest one out is about there-ish. And all the other ones are kind of in between. That's a little bit sloppy. It's a little bit more like that, roughly speaking. Even that's a little off. Right, the data is pretty good. So recognizing that the data sits kind of like that, right? Labeling the axes, putting the points where they belong, right? Just that stuff, skills that I would call middle school science level. That's 3 of the 4 points for this graph. The only point that's left is to draw a best fit line. And that can be, right, you could do something that's kind of just like that. You could extend it all the way to 0, 0, but it has to be linear, and it has to go through roughly the center of the point. So there's some freedom for exactly what that is. Right? And that's the entirety of part B. You aren't doing anything with it yet. That's part C. But you have to make a good graph first. So you get something like that. Now, how do we use it? Well, we had Snell's law from back to that page, right? This is the equation that we're going to be working with, and that tells us really what we want. So I'm going to rearrange and sort of simplify down for the situation we have. One is 1 sine theta I equals n, what we're trying to find, sine theta r, right? And so if we want this to look like, this red line is clearly a linear thing with a y-intercept of 0. So this is equation y equals mx. So let's rearrange our Snell's law to look like that. Well, this is on the y-axis, so I better get it by itself. That's y equals. And to do that, we have to divide both sides by n. So 1 over n sine theta I. Okay, and this works, right? Y equals mx. And so that means that our slope, if we could calculate the slope of this line, that will relate to the index of refraction that we want. And so to do that, all we have to do is we have to pick 2 points on the line. We know 0, 0 is on the line, so I would pick that one immediately and then pick any other point on the line, whatever that might be. It could be there. You could pick a point right there. The key is don't use your data points unless they happen to sit right on the line. Use the points on the line, right? This is delta y, delta x. So we can calculate m is delta y over delta x from those points. And if you do that, you know, again, I don't know exactly what points you're going to pick, exactly what's on your line. It's going to be probably something like this, though. So delta y is about 0.53. Delta x is about 0.78, right? This is technically minus 0 and minus 0, right? So you plug that in, you're going to get a number for the slope that's around 0.67. Then we know that the slope, right, from this connection to that, so m equals 1 over n, or n equals 1 over m, and that equals 1 over 0.67. And so then the index of refraction is about 1.5. And again, there's some variability in that. You don't have to get exactly 1.5. Depending on how good your line is, you may or may not get credit for ranges about that, but you shouldn't expect to get exactly 1.5. It depends on exactly where your data, where you think your best fit line is. The other thing, there's a couple other things to note about this question, though, before I move on. First, I got a value that's bigger than 1. That's a good sign. You can never have an index of refraction that is less than 1. If you get a value that's less than 1, that tells you that you've done something wrong immediately. If you can go back and find it, great. If not, sometimes you're stuck with it just because you want your results to be at least consistent, right? If they're consistent, then you don't get multiple point penalties. But if I thought the slope, if I had mistakenly come to the conclusion that m equals n, I would have said, right, this is not true, but if I'd come to that conclusion, I would have said that n is 0.67, that's less than 1. Immediately, I would know something is wrong and I could go back and check. The other thing to note is that there's no reason that you have to plot this on the x-axis and this on the y. You could flip them. If you flip them, then this is the equation that you're using, right? Y equals mx. And now m equals n. Your data will be different, your graph will be a little bit different, and the relationship of slope to the value you care about will be a bit different, but it will still work. So if your first instinct was to plot these on the other axis, nothing is wrong with that. It will still work out correctly as long as you sort of correctly manipulate Snell's law. Okay, so now we can move on to the second half of this question, where we deal with thin film interference. So we finished the refraction part. This is really two questions in one, right? There's no relationships between parts D and E and parts A, B, and C. So we're told now we have a light source shining on an oil film on top of water. And we're given the index of refraction of oil and the index of refraction of water. And part D is just asking at which of the two interfaces do we have that phase change on reflection happen, or phase inversion. And this is really just checking one thing. Do you know the definition of a phase change on reflection when it happens? And it happens when you go from a low index of refraction to a high. So from air to oil, we increase our index of refraction, so that one definitely happens. From oil to water, we decrease, so it does not happen there. So the only correct answer is the air-oil interface only. So that's part D. It's not asking you for an explanation, so all you have to do is just pick one of them, right? You could guess if you have no clue. You got a 1 in 4 shot. And then for part E, we have to now calculate the minimum thickness of the oil film such that the students' observations work out, right? They saw bright light when it was incident, right? Incident light at 600 nanometers. That's not the light wavelength in the oil, that's the light source. So we're going to have to do a little bit of work. So, first, we have to recognize that from part D we have one phase change on reflection, right? What we're going to be using is the path length difference equals m lambda, right? Because we want constructive, maximum in intensity. So this side first. The path length difference is given by two things. I'm going to use D for the thickness, so I don't have to write T's. So twice the thickness of the oil film, and we also have one phase change, right? This we keep just as it is because we care about the bright spot. If I wanted a destructive interference, that m would turn into m plus 1/2. Now we just need to solve this. Well, actually, before I solve it, I should note this is right. This is lambda oil. Right? That's where the extra thickness is, so we have to use the wavelength in that thickness. Now we just want to rearrange and solve. 2D equals m plus 1/2 lambda oil. And now we want the minimum possible thickness. And remember, m can be any integer from 0 on up. Since we are told that the oil really is there, we couldn't have a thickness of 0, but we can make m equal 0 because that will give us a non-zero thickness because of this factor 1/2. So m is going to be 0 to make it as small as possible. So we get 2D equals lambda oil over 2. And so we get D is lambda oil over 4. So now all I need to do is relate the incident wavelength to the oil wavelength. And you can do that by using C is lambda times F and V equals C over N and putting those together, or you can just remember the relationship that this is lambda air over N, right? Either way works as long as you arrive at that result. If you do all that and plug in the numbers, right, we get 600 times 10 to the negative 9th, and then oil is 1.43, and then we have the factor of 4. And if you plug all that in, you get 105 nanometers, or 105 times 10 to the negative 9th meters, if you leave it that way too. One thing to note as well on this, if you get part D wrong, so let's say you thought you get phase changes on both interfaces. If you thought that, right, when you came through this problem here, you wouldn't have put that in, right? And so you wouldn't have this factor of 1/2 there, and you'd pick m equals 1 instead, right? Work through all of that, you end up getting that it's just lambda oil divided by 2 instead of lambda oil divided by 4. If you've done all that, so your part E result is consistent with your part D choice of the phase change on reflection, then you get full credit for part E. So consistency is important. As long as you kind of know what you're doing and keep things consistent, you can get some stuff wrong and it doesn't hurt you very much. So obviously, ideally, right, this is the right answer, but if you made a mistake and it's a consistent mistake, you don't lose quite as many points.